Alrighty, here we go again. Ideal gases. So this is actually going to be the actual gas law that is most useful. Takes everything into account for one particular gas. This is a chunk of dry ice, which of course is carbon dioxide in its solid state, subliming, and we're going to talk about more gases. So the ideal gas law includes the number of particles, the number of moles, which is directly related to the mass, as you know. So this finally gets to what we can actually measure when we're talking, well, one of the things we can measure in the lab. Good little vid, I'll have you watch this one by Professor Dave. The gas law then, the ideal gas law includes all four variables: pressure, volume, temperature, and number of moles. So the format for this, remember, this looks like Boyle's law. Temperature's over here, and then we're throwing in this mole thing, but now we got this other variable that we haven't talked about. So the ideal gas law is PV equals nRT. PV equals nRT. Rolls right off the tongue. It's really easy to remember. And the only thing that we have to have in here to get number of moles times temperature, Kelvin, to equal pressure times volume is a little fudge factor called the ideal gas law constant. They use a capital R. I don't know why. I wish I could tell you. The numerical value is 8.31 if you use liters, kilopascals, volume in liters, pressure in kilopascals, temperature in Kelvin always, and number of moles. Now, there are other values for R. You can calculate it if you're using a different volume or a different pressure unit. You'll never use a different temperature or different moles. There's nothing other than that. So obviously there's atmospheres, there's pounds per square inch, there's millimeters of mercury for pressure, there's meters cubed, I guess you could do gallons, there's centimeters cubed, but they all end up with an 8 in them for some reason. It's kind of interesting. Anyway, do you have to memorize 8.31? No. It's super easy to calculate it though on your own. If your professor expects you to know it, you can find it for whatever volume and whatever pressure unit you're using. Here's how it goes. So PV equals nRT. What does R equal? Do a little algebra, get R by itself, put N and T on the other side, which of course requires division, P and V on top. So molar volume, we learned way back when that 1 mole of any gas at STP, remember that, is 22.4 liters. So let's put the numbers in place. In the bottom, 1 mole of any gas at 0 degrees Celsius, which is 273 Kelvin, will occupy 22.4 liters if it's at 1 atmosphere, and 1 atmosphere in kilopascals is 101.325. Push those numbers through your calculator. Pressure on the 1325, volume 22.4 liters, 1 mole, and again, 0 Celsius is 273 Kelvin. When you put that in your calculator, you will get 8.31. It's really easily calculated if you don't remember it, or if they play a mean trick on you and change pressure or change volume units. Hank is pretty silly, as you know. There's some ideal gas law problems that I will probably have you watch. And then ideal gases and real gases aren't perfect. Remember, ideal gases we assume have perfectly elastic collisions and no attractions between the particles. That, of course, is just simply hooey. So there are actually attractions in the particles, particularly when it gets really cold. So this is liquid nitrogen. If it gets really, really cold, the particles move really, really slow. They are going to be attracted to each other. Another way to get the particles really close together, besides cooling them off, of course, is increasing the pressure. So real gases aren't ideal. Nothing is, right? if there's really low temperatures or very high pressures. For most conditions in a laboratory, the ideal gas law works perfectly, but there are situations where it won't. This graph's at the end of the section showing you how different gases deviate from what they should. This one, PV equals nRT, if that came out to be 1. Sometimes they're lower, sometimes they're higher. For pressure, they're not perfect. So just know that, just like in real life, gases aren't really ideal, but they behave mostly like they are. And this is another crash course. I'm not sure if I'm going to have you watch this one or the other one. And that's it for section 3. Hope you're well.